Today we're exploring an intense what-if scenario involving the Fram2 mission, a polar orbit mission that dared to go where no one has gone before. The scenario? What if a massive coronal mass ejection hit Earth just as Fram2 was going over Earth's North Pole? We'll also talk about why in the past we've avoided humans doing a polar orbit. Stay tuned as we break down the physics, risks, and safety measures that both NASA and SpaceX rely on in these extreme conditions. I'm Ben, this is Physics or Bust. Fram2 was pushing the boundaries by operating in a polar orbit instead of the usual equatorial orbits like the International Space Station orbits in. The polar path gives us unparalleled access to Earth's surface, as well as opens up unique research opportunities. But it also exposes the crew to unique challenges, including space weather like coronal mass ejections, or CMEs. Let's get into the nuts and bolts of the threat. A coronal mass ejection is a gigantic burst of solar plasma containing high-energy protons, electrons, and heavy ions, all of which carry their own magnetic fields as the sun ejects them into space. As these particles race towards Earth, they carry with them an immense amount of kinetic energy. So why is the risk so great over the polar regions? Earth's magnetic field acts like a gigantic invisible shield, redirecting most of this harmful energy. However, near the poles, those magnetic field lines converge and open up an area where those high-energy particles are just funneled directly toward the Earth. In simple physics terms, the protection provided by the Lorentz force becomes less effective. Particles spiraling along these field lines experience much less deflection than they would at lower latitudes. As the charged particles from the CME interact with Earth's magnetic field, they create secondary effects in the ionosphere, including powerful electric currents. These currents, in turn, can destabilize satellite electronics, perturb navigation systems, and even change the flow of electric power on the ground. The atmosphere near the poles becomes like an open gate, where the normally deflected particles directly strike Earth's upper layers, including any spacecraft in the area. In the environment of a high-intensity CME, the dose rate of radiation can increase drastically. The combination of direct ionization and secondary particle showers can disrupt biological tissue almost immediately. For the Fram2 capsule operating at an altitude where Earth's magnetic shielding is at a minimum over the poles, this means an exposure that could quickly become dangerous. And just as a side note, this kind of high-intensity CME is exactly the kind of event that would create some really cool-looking northern and southern lights that could be seen from much lower latitudes. Now let's dive into what this would have meant for the Fram2 astronauts had this kind of CME happened while they were flying over the poles. There would almost certainly be radiation effects on the crew because of the high-energy proton bombardment. These energetic protons have enough force and momentum to penetrate the Dragon spacecraft's shielding. When they hit human tissue, they ionize molecules and damage cellular structures. In high enough doses, this could lead to acute radiation syndrome, symptoms ranging from nausea and vomiting to more serious neurological effects and immune system failure. Even if the crew does survive that initial radiation spike, the damage to DNA will increase the likelihood of cancer later in life. The cumulative effect of radiation on the human body is a well-studied concern in space travel, and a polar orbit exacerbates this due to the weaker magnetic shielding. Problems can also arise in the electronic systems and cause communication failures. High-energy particles can induce what's called single-event upsets in microprocessors and memory devices. Tiny errors that can cascade into massive system failure. Imagine a critical navigation computation or life support system experiencing an unexpected glitch. In extreme scenarios, these failures could force the spacecraft into a safe mode in order to protect its systems. The high-energy particles that can cause damage to hardware can also corrupt data from sensors. This results in inaccurate readings about the spacecraft's orientation, velocity, and status of onboard systems, making real-time decision-making extremely difficult because of the interference with sensors and instrumentation. A CME's impact on the ionosphere, especially over the polar regions, can severely disrupt radio frequency communication, causing a communication blackout. This kind of blackout can cut off critical links between the spacecraft and mission control, leaving the crew isolated in what might be the most dangerous part of the encounter. At the core, these malfunctions stem from the energy processes governed by electromagnetism. Charged particles, accelerated by the sun's magnetic fields, interact with Earth's magnetic topology. The reduced magnetic field strength and the geometry over the poles means that the Larmor radius, the circular path of a charged particle in a magnetic field, becomes large compared to the protective bounds normally provided by the field. This leads to a much higher probability that the particles will penetrate protective material and interact directly with both biological tissue and sensitive electronic equipment. In summary, while the Fram2 mission did push the envelope of exploration and scientific discovery, it also stepped into regions where the physics of space weather imposes severe hazards, ranging from immediate radiation harm to complex electronic malfunctions that could challenge even the most prepared crews. So why have we steered clear of putting humans on polar orbits until now? The answer lies in the balance of risk and reward. Polar orbits inherently expose both spacecraft and crew to higher levels of radiation, since they traverse the areas where Earth's magnetic field provides the least shielding. Launching into these orbits also requires some tricky trajectories and some very precise flight planning, partly in order to bypass highly dense populations during the ascent. The cumulative risk and logistical complexity have kept human missions in orbits that minimize exposure to these hazardous conditions. And rightfully so. Despite the risks, NASA and SpaceX did go through with the mission. Without advanced solar monitoring satellites like SOHO, this would have been a foolish mission to send anyone on. But at least with SOHO, potential CME events can be detected hours or even days before they actually reach Earth. While I think it was foolish for NASA and SpaceX to put the crew in harm's way like that, both agencies do put robust contingency plans in place with missions like the Fram2. For instance, in the event of a CME warning, Mission Control would be able to give the Fram2 crew a few options. If they had very little warning, they could orient the Dragon spacecraft so that the most shielded part of the Dragon spacecraft was between where the radiation would come and the crew. This could significantly reduce the amount of radiation that actually got through the shielding and to the crew. In addition to onboard shielding measures, contingency plans would have also included being able to adjust the orbit of the Dragon spacecraft in order to reduce the exposure. The effectiveness of this strategy would be highly dependent on how much time they had before the CME actually hit. The Dragon is also equipped with redundant systems and hardened electronics to try to prevent single event upsets, which is meant to ensure that even under extreme circumstances, vital systems still remain in operation. This multi-layered strategy reflects decades of research in radiation protection and electronic hardening, a testament to the intense preparation required for manned missions in the high-risk environment of space. Fram2's mission was pushing beyond our traditional boundaries and embracing new challenges. And with state-of-the-art monitoring, advanced shielding technologies, and robust contingency plans, NASA and SpaceX believe they're ready to mitigate the risks and protect the crew. However, a CME striking as the capsule passes over the poles could lead to dangerous radiation exposure and electronic failures that could be catastrophic. I highly doubt that the Dragon's shielding capabilities as well as electronics hardening have actually reached the point that it could withstand a CME and still get the crew home safe, especially since the sun is in a solar maximum where there's more likelihood for a CME to hit Earth. What are your thoughts on future polar orbits? Let me know in the comments below. If you enjoyed this video, I think you'd like this book. I have an affiliate link in the description below. I do get a small commission, but it doesn't cost you any extra. If you like this dive into physics and space, make sure to like and subscribe, and remember, keep asking questions. I'll see you on the next video.